Good day to you from Chem Help ASAP. This video is a review of the various common nucleophiles that students encounter during a typical two-semester sequence of Organic Chemistry 1 and Organic Chemistry 2. Note that this video is also effectively a review of electrophiles as well, since you can't discuss nucleophiles without covering electrophiles. The list covered in this video is not complete, but it should cover most nucleophiles and the types of reactions that use them. Of course, your instructor may include additional reactions that are not discussed in this video. If I left out one of your favorite reactions, let me know in the comments section. Finally, this video is meant to be a review and is recommended for students who have already learned some organic chemistry as opposed to beginners to the subject. Okay, so nucleophiles. A nucleophile is nucleus loving, and therefore needs a source of electron density to react in an electron-rich manner. How do we recognize an electron-rich structure? The easiest sign to look for is a negative charge. Anions, especially anions with lone pairs, are likely nucleophiles. The negative charge is literally telling you that the structure is electron-rich. Another source of electron density is any atom with a lone pair. Lone pairs can be a bit tricky if you are just learning organic chemistry. With line angle structures, you are not required to draw lone pairs, so it can be easy to forget that some of the atoms have lone pairs and are in fact nucleophilic. Finally, bonds contains electrons and therefore can serve as sources of electron density for a nucleophile. In general, we will focus on pi bonds, not sigma bonds, and these tend to be very weakly nucleophilic. Alright, let's now see some nucleophiles. We will organize them based on the type of reaction we are performing. Let's begin with nucleophiles for the SN2 reaction. This reaction is the first time that many organic students encounter nucleophiles. In the upper left corner, we have a simple SN2 reaction. Note the electrophile is specifically an alkyl halide. The carbon being attacked is an sp3 hybridized carbon. Furthermore, the carbon being attacked is neutral, so the nucleophile needs to be relatively strong to cause the attack. Okay, what are the very best SN2 nucleophiles? They are on the left: azide, cyanide, and the thiolates. They are all anions with sodium balancing the charge. Good for them. How about the good nucleophiles? They include hydroxide, the alkoxides, acetylides, and enolates. These are also anions. Why are these nucleophiles merely good and not great? These nucleophiles are indeed very reactive, but they are all also more basic. The increased basicity makes them more likely to perform an E2 reaction. On the right are some less common nucleophiles. They can all do an SN2, but they are less often seen in undergraduate organic chemistry. The most common phosphorus nucleophile is triphenylphosphine to serve the Wittig reaction. Halide SN2 nucleophiles are uncommon and mostly associated with ether cleavage reactions. Before we leave SN2 nucleophiles, I want to mention two that I personally do not emphasize with my students, but these reagents do appear in some textbooks and are covered by some instructors. The first is the use of hydride, H- as a nucleophile, typically from the use of lithium aluminum hydride. So H- hydride attacks a carbon and displaces a halide. There is no stereochemistry in this molecule, but if there were, we'd see inversion, a classic signature of an SN2 reaction. The second nucleophile is an organometallic reagent called a cuprate. To be fancy, this is a Gilman cuprate with two R groups on copper, which formerly has a negative charge, and lithium as a counterion. Cuprates can do an SN2 reaction with substitution of the halide with the R group. In this reaction, the R group is an ethyl group and the chain is extended by 2 carbons. Both of these reactions work, but they are certainly less common applications of SN2 chemistry. Let's switch to nucleophiles in the SN1 reaction. In the SN1, we are attacking a carbocation. The electrophile is positive, so the nucleophile can be much weaker. We don't need strong nucleophiles. We need weak nucleophiles. The classic SN1 nucleophiles are water, alcohols, and halides. Alkenes, which do not have a lone pair, can attack a carbocation. The product is a new carbocation, but this is still considered to be a nucleophilic attack on a carbocation. The least reactive nucleophile for carbocations may be aromatic rings. The CC pi bond in the ring can attack the carbocation, and through multiple steps we will form a product that is an example of an electrophilic aromatic substitution. This is like a Friedel-Crafts reaction. Students often want to use strong nucleophiles, for example azide, in an SN1 reaction. Strong nucleophiles are not typically compatible with the reaction conditions that form carbocations, so you will almost never see carbocations reacting with strong nucleophiles. Nucleophiles react with epoxides to open the ring. I'm showing a terminal epoxide formed from a terminal alkene. Terminal epoxides have 2 different sides, and whether the opening occurs on one side or the other gives regioisomeric products. The type of nucleophile determines which product is formed. Strong nucleophiles that you associate with SN2 reactions, azide and alkoxides, tend to favor the nucleophile attacking the end carbon of the epoxide. Weak nucleophiles associated with an SN1 reaction, water and alcohols, give the other regioisomer. The opening of epoxides with weak nucleophiles normally occurs under acidic conditions. This now completes our discussion of nucleophiles that attack sp3 hybridized carbons. For the rest of the video, we will discuss reactions at sp2 hybridized carbons. Many of the nucleophiles that attack sp3 carbons will also be useful for sp2 carbons, but just because a nucleophile is strong in terms of an SN2 reaction does not mean it is a strong nucleophile for all reactions. Let's now look at nucleophiles that attack carbonyls, namely aldehydes and ketones. The nucleophile attacks and forms an anionic tetrahedral intermediate, which is typically protonated in a later step to give an alcohol addition product. Carbonyls are weak electrophiles. The carbon being attacked is neutral. The nucleophile therefore must be strong. The best nucleophiles for these reactions are the organometallics, like a Grignard reagent, and the hydride reagents. Enolates are also excellent carbonyl nucleophiles. In general, the nucleophilic attack is irreversible, or at least very strongly favors the tetrahedral intermediate. Favoring the intermediate requires an unstable, highly reactive nucleophile. This is interesting because we saw a lot of strong nucleophiles in the SN2 reaction. Why aren't these nucleophiles mentioned on this slide? Let's see. I'm showing methoxide as the nucleophile in this reaction. Methoxide can certainly be a strong nucleophile for an SN2 reaction. It can also attack a carbonyl to make a tetrahedral intermediate. The problem is the strong nucleophile can be kicked right back out by the oxyanion. This first step is rapidly reversible, and the position of the equilibrium favors the starting carbonyl. That is why the classic SN2 nucleophiles are not very effective in attacking a carbonyl. Not all carbonyl attacks involve a neutral carbonyl. When protonated, a carbonyl becomes a very strong electrophile, so the nucleophile no longer needs to be strong. The best nucleophiles for a protonated carbonyl include water, alcohols, which form ketals and acetals with loss of water, amines, which can make imines or enamines, and finally enols in the acid-catalyzed aldol. The reaction of acid derivatives with nucleophiles gives different products depending on the identity of the nucleophile. Very strong nucleophiles like hydrides and organometallics perform both a nucleophilic substitution and nucleophilic addition to give an alcohol product. Weaker nucleophiles like alcohols and amines tend to undergo an acyl transfer reaction to give a new, more stable acid derivative. The exact product can vary based on what type of acid derivative is being used as the starting material. Closely related to carbonyl addition chemistry is the reaction of alpha beta unsaturated ketones with nucleophiles. Many stronger nucleophiles simply attack at the carbonyl carbon. Weaker nucleophiles instead can react at the beta carbon to give the Michael or conjugate addition product. The best nucleophiles for this kind of reaction include amines, thiolates, it's a sulfur nucleophile, and stabilized enolates. Stabilized enolates are carbanions that are attached to two electron withdrawing groups. Functional groups like beta-ketoesters can be deprotonated to form an enolate that is attached to two carbonyls, two electron withdrawing groups. This type of enolate is a very mild nucleophile that is ideal for performing a Michael addition onto the beta carbon of an alpha-beta unsaturated ketone. Finally, let's look at nucleophiles that attack carbons in an aromatic ring. These reactions are nucleophilic aromatic substitutions, NAS or SNAR. These reactions are set up with an aromatic ring that bears a halogen, ideally a fluoro group, as well as one or more properly placed electron withdrawing groups. This notation, with a line coming off the ring, indicates that the ring has an EWG somewhere on the ring, without committing to where the EWG is actually attached. Ideally, we want the EWG to be either ortho or para relative to the leaving group. The nucleophile attacks to make something called a Meisenheimer complex. This unstable anionic intermediate decomposes with loss of the leaving group to restore the aromaticity of the ring, now bearing the nucleophile. The best nucleophiles for this reaction are typically alkoxides and amines. Surprisingly, the organometallics, like Grignards, are not good for this reaction. The issue is that the organometallics tend to react with the electron withdrawing groups before attacking the ring. Organometallics react, but the reaction occurs in the wrong place and does not give the aromatic substitution product. That was a short review of common nucleophiles and electrophiles that students often see in Organic 1 and 2. I hope it was helpful for you. Please leave a comment, leave a like, or subscribe to the channel. Take care.